In this video, we will discuss about versatile nature of carbon. So in the previous video, we saw the formation of covalent bonds by sharing electrons. We also drew a few electron dot structures which clearly show the sharing of electrons, how electrons are shared between atoms present in a compound. In the beginning, we saw that almost everything around us is made of carbon, including us. Scientists found out that there were more than 3 million carbon compounds. But how is that actually possible? How can carbon do such a great thing? How can it combine with so many? So carbon has a unique ability to form bonds with other atoms of carbon to give large molecules. And this particular property is called catenation. So what exactly is catenation? The property of self-combination of carbon atoms to form long chains is called catenation. These long chain of carbons can be long, branched or rings. So carbon will attach with several other carbons to form long chains which can be branched, also form rings. So if you can see here, it is a very long chain of carbon. See, here carbons are attached, carbon, 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 carbon. So all the carbons are attached in a long chain. While here you can see carbons are attached in the form of rings. Carbon, 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 carbon. It is in the form of a pentagon. Here you can see a hexagon. This is also a hexagon. See, they are arranged in the form of rings. Carbon attached to each other in the form of rings. Here you can see the branches. See, this is a ring and you will observe the branching here. So carbon, carbon, carbon. So you can see the branches. So these are the various ways in which carbon attaches to another carbon atom to form long chains which can be branched or also in the form of rings. Carbons are linked to each other by single, double and triple bonds. So based on the bonding, they are classified into saturated and unsaturated hydrocarbons. Oh, two new words introduced. So these are the carbons which are bonded to others. See, here you can see they are bonded with just single bonds. You can see carbon bonded to hydrogens with just single bonds. But here when you see in this case, you can see carbon bonded to other carbon in triple bond. So you can see triple bond and you also can observe single bonds. But in this example, you can see double bonds. Carbon attached to another carbon with double bond. You can also see single bonds in between. So carbon is attached to others by single, double and triple bonds. So based on this attachment, it is classified into saturated and unsaturated. So what actually is saturated hydrocarbon? A hydrocarbon in which the carbon atoms are connected only by a single covalent bond are called saturated hydrocarbons. Example, alkanes. So if there are just single bonds present between the hydrogens, then they are called saturated hydrocarbons. Example, see here in all these compounds, the carbons are attached with other atoms with just single bonds. See, you can never spot any double or triple bond in these examples. So they are just single bonds. Hence, they are called saturated hydrocarbons. So a hydrocarbon in which the carbon atom is connected to others by just single bond, they are called saturated hydrocarbon. So the example are alkanes. So alkanes are the structures which have only single bonds and they are saturated ones. So then what is unsaturated hydrocarbon? So what is an unsaturated hydrocarbon? A hydrocarbon in which the carbon atoms are connected by either a double or a triple covalent bond are called unsaturated hydrocarbons. Example, alkenes and alkynes. So if a hydrocarbon which contains carbon and hydrogens are connected by either a double or a triple covalent bond, then they are called unsaturated hydrocarbons. Let us take an example. So here in this particular figure, you can see the topmost structures have double bonds between the carbons, and the double bonds signify that they are alkenes, and the lower structures have triple bond between the two carbons and they signify alkynes. So both having double and triple bonds are unsaturated hydrocarbons. No other element except carbon exhibits catenation to this extent. So, binding up to the atoms of its own to form long chains. So, this particular property called catenation is exhibited to this great extent just by carbon, and no other element can actually exhibit the same property. But silicon also forms some compounds with hydrogens which have chains up to 7 to 8 atoms, but they are very reactive. But the carbon-carbon bond is very strong and hence very stable. Hence, a large number of carbons are linked to each other. So, silicon also has a particular property that is similar to the catenation of carbon, and it can also join and form compounds with hydrogens up to 7 to 8 atoms, but they are very reactive. But carbon-carbon bond is not like that. It is very strong and stable. So a large number of carbons are linked to each other to form large chains. See, here you can see silicon which is forming bonds with hydrogens. So these are actually silicon that is forming compounds with hydrogen, and the chain will extend just up to 7 to 8 atoms. But all these three components are very reactive. Apart from catenation, another feature that carbon has is tetravalency. We all know that is carbon has a valency 4. Hence, each carbon can form bond with 4 carbons or other monovalent elements to satisfy the valency. Carbon forms bond with oxygen, hydrogen, nitrogen, sulfur and several other elements, giving rise to different components because of the property catenation. See, you can see here the structures where carbon, this particular end, tips, corners of all these structures are carbon. So this is carbon, carbon. So this is also carbon, carbon. All these tips are carbons. So it is forming bonds with nitrogen, it is forming bonds with oxygen, and there are also structures like hydrogen, bromine, chlorine. So it forms bonds with almost different elements. The most interesting part is that the bonds formed by carbon with other compounds are also very strong and hence exceptionally stable. One reason for the formation of strong bonds by carbon is its small size. This is very important because the small size of carbon is enhancing it to actually form strong bonds with other elements. This enables the nucleus to hold the shared pair of electrons strongly while the large atoms have weak bonds. So this can be explained very simply. If it is a large sized atom, the difference that is between the two atoms, the nuclear difference between the two atoms is very large. Hence, it is very easy to break the bond. But if the atom is small in size, then the difference between the nucleus of both the atom is very small. Hence, it requires a lot of energy to break that bond. Hence, the carbon, due to its small size, forms exceptionally stable and strong bonds with other compounds. See, for an example, if we imagine this is carbon and it is forming a bond with another element, the distance between this nuclei and this nuclei, if it is very small, then it is very difficult to break. The bond is so stable and strong. But just imagine if this is one random atom and it is attached to this atom. There is a large distance between the nucleus of this atom and the nucleus of this because it is a very large atom. Hence, it is very easy to break the bond and it is not so stable. So that is how the small size of carbon is actually helping it to form extra strong and stable bonds. Do you know the two characters observed in carbon, that is catenation and tetravalency, put together gives a large number of compounds? And the scientists have already proved that there are more than 3 million carbon compounds. Many have the same non carbon atom or group of atoms attached to different carbon chains. These were initially extracted from the natural substances and thought that these compounds could be formed only within a living system. But this was proved wrong when the scientist named Friedrich Wöhler disproved this by preparing urea from ammonium cyanide. So initially, many have believed that these carbon compounds, non-carbon atoms that are attached to others, forming different carbon chains, were only extracted from natural substances. They thought that they can't be prepared from chemicals. They have to be formed only within the living system. But a scientist named Friedrich Wöhler, so this is the Friedrich Wöhler, he disproved it and proved it wrong. He prepared urea, a carbon compound, from ammonium cyanide, which is a chemical, a non-living substance. So this is urea with the formula C double bond O, C single bond N H2, single bond N H2. So by this discovery, he proved that carbon compounds can also be formed from chemicals, not only from the living system. Thank you.